way to achieve that is actually not nearly as complex as you might think. Lights back on. What you do is you draw what's called an occlusion map. You draw everything in the scene black, except for the sun. I drew the color of that glare you see. Just the one solid color. So everything's solid color black and the sun's solid color. And you end up with, basically just a scene like this. Filled circle. Then you apply radial blur. Radial blur is you have a center point and you stretch everything outwards. And that's it. So then after that, if a planet happens to be in front of the sun, it'll be somewhere like here. But because it's all black, it'll show up like this. And when you apply the radial blur, here you'll have really long rays, and here you'll have really short ones, because there's not a whole lot of sun to blur away. That's all it is. And that's also why you'll notice that when a planet is, let's say this is the center of the sun, if a planet is just beyond the center of the sun like that, it has a really nice way of it does rays over the planet, which looks really nice, but as soon as the planet crosses the center of the sun, the center is in here, it completely stifles the rays. You can actually see it right here. Like you see, it's over the planet, and then immediately it stops being over the planet. And then it's going to slowly move away, and then it starts bleeding on the planet again. So that's why it looks that way. Like I didn't do any kind of shadow volume or anything. It's really just a simple post-processing effect. You just re-render there. And actually the clicking is done very much the same way. If you click on a planet, the way you know which planet you clicked on, you draw every planet. Well, you draw, you clear the background with black, draw every planet a different color. And then you find out where you clicked. And then you sample that pixel on the texture where all the planets are unique colors. You find out what color that pixel is, and voila, you know what planet you just clicked. Which sounds extremely inefficient. I wanted to be able to render just the point you clicked, but this is way easier. There's also an example in the book that does exactly that. There you go. Yeah. And I think that's about it.
Yeah, I think we covered it.
How do you split the work, guys?
Essentially, I had a much lighter course load, so I did all the graphical stuff.
And so I did all the interaction stuff on the mouse movement and
mouse movement, the detection,
keyboard interaction,
timeline control.
Yeah.
Concerning the moon, is it also on logarithmic scale, concerning the distance from Earth?
Oh.
Or did you just put it there randomly?
Yeah, actually, I did this just before we presented. See, if you keep it on the logarithmic scale, it's like completely inside the Earth. Because, it's insanely close to the Earth compared to how close the planets are to each other. So you just artificially bump up the distance. Because actually what happens is I stored all of these objects in relative units. All of the distances between planets are stored in, I think they're astronomical units, distance between the Earth and the Sun. AU, yeah. And all of the diameters of the planets are stored as multiplier to the diameter of the Sun. So then after that, there's a simple so as you can see, a lot of textures. All of those green icons, all textures. But let's see. Actually, this is where all the planets are created. You can see they're all relative units. You can kind of recognize it. Well, if it's astronomical units, the Earth is 1 times the distance from the Earth and the Sun, from the Sun. And its period, well, not very surprisingly, has 365, which is roughly a year. And then after that, the tilt is slightly different. Here, the rotation period is stored in hours. Of course, I've just pulled all of those things off Wikipedia. And actually, you can see what I did here is I did just slightly bump this up and I slightly dimmed this down.
Wait.
No, I think I actually bumped it up, then I divided by something. I'm not sure what I did. Anyways, I artificially modified the moon so it would be visible. And the, what was I looking for? Which code? Right here. This little thing right here is where all the scales are done. So as you can see, divide is just some dividend over a value in this logarithmic scale. You just apply the log function. So whatever the value, the variable value here is whatever value I have in the data structure that I showed earlier, that's stored in relative units. So use a logarithmic scale for the distance and a logarithmic scale for the diameters of the planets, and just linear for the speeds, because they're all stored in period, and I wanted the frequency, opposite period? Yeah, one is the speed, which is frequency, yeah.
So frequencies are realistic, right? So
yeah, actually, yeah, part of the motivation for having them all as periods instead of frequency is that because of the whole way this is controlled by a timeline, you can actually see the timeline controller right here. It just has a time flow variable that you can either set or multiply by something, or this is the pause functionality right there. Oh, and a small side note, when every time you restart, I just randomly see the time. This is the time as far as the model is concerned. So whenever the page reloads, you just generate a random time between 0 and 1,000. And so that the planets are randomly spread, because originally, whenever you refresh, all the planets are in a line every single time, which is not super realistic, because that does not happen very often. And yeah, this is like literally right here, the time that all the rotations are based on. You get the elapsed time multiplied by the time flow, and you divide it by 1,000 because they're in milliseconds. Oh, wait, not because they're in milliseconds, just to make it more realistic. Implementation detail.
So how hard would it be to have the night map on the Earth when the moon occludes it from the sun?
Extremely difficult.
Okay.
just for fun. Yeah. Well, seriously, it would be, because you would have to get into shadow volumes and stuff. Because otherwise, you would need to project every planet onto every other planet.
Oh, just Moon Earth.
Oh, Moon Earth.
combination.
Well, I guess if you're just going for those two, it might not be that hard. I mean,
Okay, you have 10 seconds. Can you do that? No, just kidding.
no. One thing that's kind of fun is that in this thing, they're all it's all modular. So if you just take this planet there right here, you reload, then that planet just doesn't exist anymore.
You kill the planet?
Yeah, just for fun.
Which one?
Which one? Kills Mars and
Jupiter.
Yeah, Jupiter is not important.
And if you want to see little experiment.
Are you predicting Saturn?
Yeah, does Saturn have rings?
Oh, yeah, 2 of them have rings.
Cool.
I actually have the textures for them and everything, but they were not done.
Okay. Future war.
Yeah. Well, what happened is rendering Earth took almost all the time because it was so complicated with all the textures. Actually, I had 2 extra textures for the Earth that were not used, which were the cloud map and the cloud transparency map.
Yeah.
So yeah, we have a lot of data for Earth. Actually, 2 of the planets they don't have real textures. One of them is based on one of Saturn's moons, I think. And the other one, I'm not even sure. I think it was entirely fabricated.
Apparently nobody's an astronomer here. Ah, maybe you are, so you can tell us.
It's not relevant.
Yeah?
I'm wondering how you stored the bump maps.
Oh, they're, actually, yeah, I used it, wait.
Oh, they have the filters
You can actually look at them as textures, they're just textures. For example, oh, no, that's a color map. Well, as you can see, a lot of freaking holes. And if you look at, well, this is the height map that I got. And this, if you were looking for geometry displacement, this is what you would use. It would allow the sphere to be, properly shape, but the problem that happens here is if you have one vertex end up here and one vertex end up here and none in between, you'll notice that there's a lot of detail missing. Because if you're talking about geometry displacement, if you have one vertex here, and nothing in the middle, you can't represent that in any way. That's not very, you know, it doesn't produce nice results. However, if you use the normal map, which is this, it's pretty neat. What happens is each one of these has, oh yeah, actually, how do you do the bump map? At every point, what you do is you take the normal and the up vector of the sphere itself. If you get the dot product of these two, you end up with this vector, the tangent vector. And then you take the dot product of these two and you end up with the vector that points this way. And what this does is every color component, all three color components, match to one of these vectors, or one of the three vectors. So if you take a different point that's more useful in a 2D, let's say I take this point, it has a normal pointing this way. This is the up vector. The dot product of these two would generate something about here, and the dot product of those two would generate something about here. So you take the red multiplied by one of these, the blue multiplied by another, and the green multiplied by the third, and it takes your normal and it just offsets it slightly. So that instead of having a sphere that looks like this everywhere, you have a sphere that looks, the normals are normal, but then after that, if you see a hill, it'll slightly bump. It'll do bumps like this, where when it's slanting this way, it makes it look like if the planet is rising, like if there's an uphill, and when it's slanted the other way, it looks like there's a downhill. When the geometry didn't change, you just picked clever colors.
So this is bluish because blue is the Z and Z is the one that you have from.
Z, blue is how much of the normal.
So a perfect sphere could have completely blue.
Yeah, the perfect sphere would have a completely blue normal.